So, chapter 3 is all about exponential functions and logarithmic functions. Okay? I don't care how you did last year on this stuff. Today's a new day. Today's a new school year. It doesn't matter how you did last year on exponents and logarithms. Okay? I will tell you that we will get to use our calculators in part of this chapter. So both our quiz Thursday and our test Friday will be a calculator portion and a non-calculator portion. Okay? So a to the x is an exponential function as long as a is greater than 0 and not 1. Okay? So we have a number raised to the power. It is not a variable raised to a power. It's a number raised to a variable. Do you see how that's different? Okay. Our variable is in the exponent, and our base is a number. Okay. Can anybody show me with their arms what the graph of an exponential function looks like? Do you remember? We have exponential growth and exponential decay. Does that ring a bell? I mean, maybe in science class we've at least talked about this a little bit, right? Okay. If we have a positive exponent, we're going to grow. If we, grow. If we have a negative exponent, we are going to decay. All right? So a to the x, we have a positive exponent, we will grow. A to the negative x, we have a negative exponent, so we are going to decay, is the word you like to use. Okay. Just throwing things, not a big deal.
Yeah, I guess so.
Okay. Okay. I have like this red dotted line right here. What is that? It is the x-axis, but what's on the x-axis? An asymptote. Y equals 0 is a horizontal asymptote for our parent function. Okay, yes, I did say parent function. Okay, can you take a number and raise it to a power and get a negative number? You cannot. Because if you have a negative exponent, like 4 to the negative 2, right? That's just the same thing, like 4 to the negative 2 is 1 over 4 squared. Okay? Still going to be a positive number. All right? So, we have this asymptote here that's basically protecting all of those negative values because we're not ever going to get there. We can't even get a 0 out of the deal. Okay? So all of our numbers will be positive. Okay? For both of these graphs, what's the range?
For growth, it goes from, 0, because that's our asymptote to infinity, and then for our decay, it goes from negative infinity to 0.
This right here?
Oh, infinity to 0.
Okay, what did you say, that they're both above 0?
Yeah.
Okay, so no matter if it's growth or decay, our range is 0 to infinity. Basically, the horizontal asymptote and above, right? And since we have a horizontal asymptote, we better not include that number. Okay? What about our domain? What's our domain? Yeah, all real numbers. Okay? We can plug anything into an exponential function, not a problem. Okay? Notice how our parent function does have a y-intercept of 0, 1. Okay, let's talk about y. What is anything to the 0 power? 1. So our parent graph is going to have an y-intercept of 1. Okay. So let's talk about my expectations for when you graph an exponential function. I don't think these should take a big chunk of your time, okay? I'm all about graphing efficient, okay? So let's talk about the efficient way to get these graphed, okay? I understand that maybe my expectations are slightly different than your teacher's last year, okay? And you can ask me questions about that if you think that it's like completely different, okay? But this is what I think is going to be the most efficient way for us. So we're going to graph f of x equals 3 to the x. Okay? And when we're talking about a parent function, these are the 3 values I want you to plug into your parent function. -1, 0, and 1. These are the 3 easiest values to plug in, and they're going to give us enough information to give us a good shape. Okay? So, if we plug these in, what's 3 to the 1? Okay. What's 3 to the 0?
1.
And what is 3 to the -1? It's the same thing as 1 over 3. Okay? Those are nice numbers, right? We don't have to think too hard to get those. Okay? So we can plot 1, 3, 0, 1, and -1, 1/3. Okay. We have our horizontal asymptote of y equals 0. And then we want to make sure that we have a nice curve that approaches our horizontal asymptote. With every graph, I'm going to ask you for the domain and range. Okay, that shouldn't be too strange. We've been doing this for a while. Okay. Hayden, what's our domain? Okay. Jack, what's our range?
0 to
Okay. Now, chances of me asking you for a parent graph on Thursday's quiz or next Friday's test, like 0% chance. Okay. So let's talk about, yes.
And different question. Why is it when you put in 0? Why is it 1 again?
Because 3 to the 0 power is 1.
It's just everything is 1.
Just anything to the 0 power is 1. Mm-hmm. You don't need to write this down, but let's just remember from our chapter 1 days. If I have something multiplied to the outside of our function, how does that affect it? It's a stretch or a shrink vertically, right? Inside of our function, if I have a number added or subtracted, which way are we going to shift? Left or right. And if we have a number on the outside of our function, then it's going to shift us up or down, okay? Remember, a negative on the outside means we reflect about the x-axis. A negative on the inside would make us reflect about the y-axis, okay? Now, I do want to point out that if we are talking about an exponential function, inside the function would be in our exponent. So if you have numbers in with your exponent, that's inside the function. And anything after or before, okay, would be considered outside of the function. Okay? For example, we are going to graph 3 to the x plus 1. Go ahead and write it down. G of x equals 3 to the x plus 1. plus 1, is it inside or outside of our function? Okay, it's inside of our function. And if it's inside of our function, Emma, which way are we going to shift? Okay, so this means we're taking 3 to the x and shifting left 1. Okay, so we already know that our parent function has coordinates of -1, 1/3, 0, 1, and 1, 3. We just graphed it, okay? But if we hadn't just graphed it, I would suggest writing this table of values down, okay? It doesn't take us much thought, all right? Those are pretty quick values. And then what we can do is we can say, all right, well, to get 3 to the x plus 1, we need to shift those left 1. So if I'm at -3, 1/3 and I shift it left 1, what does that coordinate become?
-2, 1/3.
-2, 1/3. And if I'm at 0, 1 and I shift to the left 1,
-1.
-1, 1. And last but not least, if I'm at 1, 3 and I shift,
That would be 0. On your XY, you made the first number -3 instead of -2.
oh, it needed to be -2. I was excited about that 1/3 apparently. Okay. Now, did our horizontal asymptote, did that move at all? If we take a horizontal line and we shift left 1, did it really go anywhere? Okay, so we would still have a horizontal asymptote at y equals 0. Okay. Which means our domain and range are unaffected. Our domain is always going to be all real numbers, and our range is always going to depend on our horizontal asymptote. And since our horizontal asymptote didn't change and we didn't have any sort of a reflection, our range can still be 0 to infinity. Okay, we're going to do one more graph. Ready? Okay. G of x equals 5 to the x minus 3 minus 2. I want you to first take 30 seconds and at your pod decide what sort of transformations this graph has compared to 5 to the x. Okay, 30 seconds. Okay, so our parent function is 5 to the x. And I do want you to think about the coordinates on the parent function. It's pretty quick, right? On our parent function, I want you to think about -1, 0, 1. Okay? Well, what's 5 to the 1? 5. What's 5 to the 0? 1. What's 5 to the -1? 1/5. Okay? There's our parent function. With those coordinates, we need to get to 5 to the x minus 3 minus 2. Okay? That at 5 to the x minus 3 minus 2. Okay? Ryan, what is happening? Where are we going? Okay? So we're going right 3 and down 2. Are you okay if I write it like that? Just a little note to myself. Okay? Whew. So we're taking -1, 1/5, and we are going right 3 and down 2. So I'm going to plot it I'm going to say, well, we went over to the right to 2, and then we went down. How would you describe that number, that y value? Okay, negative 1 4/5. And you know my great dislike for mixed numbers, but I will allow it in this graphic. Okay, it's just going to be easier for us. Okay, we basically took 1/5. We went down 2, so we went down to negative 1 4/5. Okay, our coordinate 0, 1. If we shift right 3 and down 2, there's our coordinate. Where did we end up? Looks like 3, negative 1. Okay. And then 1, 5. If we shift right 3 and down 2, there's our coordinate right there. And it looks like we shifted to 4, 3. So now I'm going to draw my horizontal asymptote at y equals 0. No. Okay, our entire graph got shifted right 3 and then down 2. Okay, so where does our horizontal asymptote end up? Okay, y equals negative 2. Okay, so at your pod together, go ahead and identify the domain and range for this graph. Reagan, what's our domain? All real numbers. Veronica, what's our range? I love it. Okay. One last thing. I'm going to ask you for the y-intercept. We will always have a y-intercept with our graphs. Okay. In general, no matter what function we are talking about, how do we identify the y-intercept? We need to plug 0 in for x. Okay. So if we want the y-intercept, okay, we are going to plug a 0 in for x. Okay. Well, we end up with 5 to the negative 3 minus 2. Well, what does 5 to the negative 3 mean? 1 over 125. And then minus 2. Our y-intercept would be negative 1, 124, 125. Would you agree? Okay. I'm okay with mixed numbers on these. In your opinion, do you think this is going to be on the non-calculator or the calculator portion of your quiz and test? This is going to be on the non-calculator portion. I need you to be able to come up with these graphs based on the relationships without your calculator. Okay? It's just, that's fact. All right? All right, let's talk about the number e. We have the number pi. We also have the number e. Some awkward, I know, the number e. Okay. But it is what it is. Okay? E is what we call the natural base. Tomorrow we'll talk about the natural log. Probably a relationship here, right? E is called the natural base. Anybody remember approximately what it is? Okay? That's pretty good. 2.718. Okay? Just like pi, e is an irrational number, and it is about 2.718, blah, 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 blah. It's irrational, so it keeps going. All right? Get out your calculator when you're done writing this down, and I want you to find your e button. You should have like e to the x on your calculator. I want you to find it. And plug in e to the 1 to make sure that you get 2.718. It should be towards the left. I think it's a button that you have to press second to get. Like I think it's with the natural log. Okay? LN means natural log. Okay? Log natural. Right? Okay, LN is the natural log button. If you press second and then that button, you should get an e to a power. Is anybody having trouble finding it? Did e to the 1 come up with 2.718? Blah, 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 blah. Okay? Try e to the 5. Big number? Okay. So our e to the x graph is going to have the same properties as our other ones. Our coordinates are just going to be irrational. So when we graph e to the x, okay, if we stick with our 0, 1, 0 setup, okay, we're still getting e to the 1 is e to the 0 is 1, and e to the negative 1 is 1 over e, just like we would for base 3, base 5, base 1500 if we wanted to. Okay? But in order to plot these, we need to at least know their approximation, which means you're going to have to use your calculator to help you out. All right? We know that e is approximately 2.7. What's 1 over e approximately, or e to the negative 1 when you put it in your calculator?
1 over 2.
Okay, well, I need to know what that is. Put in your calculator, e to the negative 1. 0.367. It would be to your benefit to remember that e to the x looks like this and e to the negative x looks like this. Okay, how many of you have worked with growth and decay in your science classes? Okay, we are going to work with it a little bit more next Tuesday, but it is an important part of biology class. Would that be biology, physical science? Probably the biology part of it. Okay, biology is where you would see that. All right, now you ready for your calculator part? Oh, I think you are. I think you are. Compound interest. Does that look familiar? Okay. This is something that I know is familiar from last year. And you can probably guess what I have covered up on the right. What equation do I have covered up on the right? What goes along with this? Okay, we'll get there. All right.
Oh, it's like constant compounding, right?
Yep. Per? Okay, we'll get there. So compound interest, super applicable. Loans, savings accounts. Okay, really, when we're talking about money, all right, interest has to be calculated so many times, okay? And so if it's calculated a certain number of times per year, we have to use this compound interest formula, where A is the amount you get after you have an initial principal, number of times you compounded per year, rate, and time Please make a note, time always has to be in years. So if it's not years, you would have to adjust that. Like if I say 36 months,
3 years.
time would be 3. Okay? Okay? How many of you drive a car? Okay? If you don't have enough money to buy your car outright, you have to take out a loan. And when you take out a loan, you have to pay interest as you pay back that loan. It follows one of these, okay? Either this one or the one I'm about to show you, okay? If you have a savings account, typically savings accounts earn interest, okay? You make money on the money that's just sitting there, okay? That is calculated by using one of these formulas, okay? And depending on which loan you get or which savings account you choose will depend on which formula it's used and what N is, okay? So N is the number of times compounded per year. Annually would mean N is 1. Monthly would mean N is 12. Weekly would mean N is 52. There's 52 weeks in a year, right? Okay. Daily would be 365. 366 next year, though, right? We have a leap year, 2020. Is that right? Yeah. We won't worry about leap year. Okay, just worry about normal years. Okay. Now, this is if we're compounded a certain number of times per year. But if we're compounded continuously, then we get to use PERT. P-E to the R-T. And all of these stand for the same thing. So you wouldn't even have to rewrite these down. You can just write, same as before. Okay, if you wish. Or if you want to write them all down, I'm not going to stop you. Okay? But what we're going to have to do is we're going to have to decide which formula to use when and where to plug in what numbers. That's really the gist of it. So these problems are definitely going to have to be on your calculator portion on Thursday. Okay, what's going to happen is you're going to get, on Thursday's quiz, you're going to get a half sheet of paper that you're not going to use your calculator on. You're going to turn it in, and then you get a half sheet of paper that you can get your calculator out and use it. Okay? All right, so what I'm going to have you do, I know that this seems silly, but go ahead and write write all of the words. Okay, don't just write 12,000, 9%, 5 years. I want you to write all of it so that when you go back and use your notes to help you in your homework, you actually know what the problem said. So you can help decipher what you need to do in the problem you're working on. Okay. So what we're first going to do is figure out what our balance is when we are compounded quarterly. Okay. Thank you for asking that question. So you are always going to see annual interest rate. That just means your interest rate doesn't change for those years. Like every year the interest rate is 9%. But how many times it's compounded is separate from that. So how many times is it? Yes, and thank you, because that's a good thing to point out. You're always going to see annual interest rate, okay? But compounded, whatever is with compounded tells you what formula to use. So since we're being compounded a certain number of times in a year, we need to use A equals P times 1 plus, is it R? Raised to the NT? R over N, inside. Thank you. That one's better. I knew it wasn't just R, but it wasn't. Okay. So, what we have are, whatever we begin with is our principal. So, 12,000 is our principal. That's how much we put into our savings account. Or if you had a loan, that's how much you took it out for. Is our rate 9? No, you need to always change it to a decimal. Your rate is 0.09. Quarterly would mean how many times per year? 4. There's 4 quarters in a dollar. There's 4 quarters in a year. So N is R, and we're talking about 5 years. So T would be 5. Okay, ladies and gentlemen, you have a really nice calculator sitting in front of you. Okay, I would maybe go ahead and change this to 20, but type this in all at once, exactly how you see it, except just make your exponent 20 instead of 4 times 5. Don't try to do this all in separate steps. Plug it in exactly how you see it, and your calculator will take care of the order of operations. Okay, you get 1,800 what?
726.11.
0.11?
Yeah.
We all agree with that? Okay, it is what?
Dollars.
Okay, it's money. So number 1, 2 decimal places. Number 2, put a dollar sign. Okay. Now, let's calculate it if our interest is compounded continuously. Before we plug it in, is this going to give us a higher amount or a lower amount? We are compounding more often, which means we're going to gain more on our interest. Okay? So compounded continuously means PERT, P, E to the RT. So our amount is going to be 12,000 times E to our rate times time. Okay? If you are putting money into a savings account, you want your interest to be compounded more often than not. If you're taking out a loan, you want the least amount of compounding possible, so it's not calculated quite as often. Okay, what do we get here? We have money. 18,000, I bet?
819.
819.75. Because you put in 1,200 instead of 12,000. Okay, please listen. Graphing, no calculator. Problems like your warm-up, no calculator. Compound interest, yes calculator. Have a wonderful day.